Welcome back from the break. I hope it was a refreshing break and that you're ready for the next part. In this part we will start analyzing the energy demand for a vehicle, and we will start talking about the energy system in more detail. When we talk about the energy system, we have a complete system from the primary sources to the usages, and in this case we're working with vehicles, so we have a driving mission at the end case. So we're following the energy from its primary sources down to the tank where we're storing the energy, and then inside the vehicle it is converted to energy that will propel the vehicle so that the vehicle will roll forward. And this analysis that we will do will have a cut here at the wheels, so we'll look at this is the powertrain, what it's doing, and then we're following what is the vehicle doing and what is, for example, the speed profile that we're following. When we look at a certain driving mission, this driving mission will result in a minimum energy requirement. This minimum energy requirement will result in a minimum energy requirement here at the wheels. It will depend on the design of the vehicle, the weight of the vehicle, and the rolling conditions that we have on the vehicle. When we have this minimum energy requirement here, it is the purpose of the powertrain or the vehicle propulsion system to generate that torque so that we are propelling the vehicle. And with this backcasting, we're looking at what do we want to achieve, and then we're thinking backwards, what does it cost in terms of different resources. And that's one of the things that we will look at in the next point. So down here we have this minimum energy requirement that is manifested by this equation, and we can see the energy flows which is going along the arrows, but when we do the analysis we start down and we do this bottom-up backcasting. We have this driving mission, and then we have different options. We can select a diesel engine or a gasoline engine, or we could have an electric drive, and then we can propagate up. If we have the electric drive, we could do it either with a fuel cell vehicle, or we can do battery, where the electrical energy come from. For example, it can come from either renewables or it can come from other types of sources. So we have the sources fossil fuels, oil, which is the thing that we are most accustomed to in the vehicles. Then we have natural gas, we have coal, where we can take energy and use it in different paths down. For the vehicle part and the diesel engine, we can go up here and see what kind of CO2 numbers will we get by different options. So this is an overview that can be used in back of the envelope calculations to analyze how much energy does a certain powertrain solution give rise to. We'll look a little bit more on the different links in the energy chain, and then we will come to the question and use two of my favorite examples to explain why have we ended up with liquid hydrocarbons and what is making it so difficult to exchange the liquid hydrocarbons for something else. The energy system overview. We have primary sources, we have all the different options from the primary energy sources to the onboard storage. When we talk about the primary energy sources, there are a few sources, but there are many options. For example, we have oil, natural gas, or coal, that is carbon that's in the ground. These sources are limited. We know that there is not a finite amount of carbon in the ground, so oil wells as we know them today will be depleted. Still, there is much usable carbon in the ground, not only in oil wells, but also in coal, etc. The thing that we know is that the cost will increase to extract more of it, but right now we have a situation where there is not so much demand, so the price is not increasing due to the drop in demand instead. But it will be more expensive to extract the oil in the future. Coming to the other part, nuclear power, we have a lot of fission material available and we have a lot of fusion material available. When it comes to solar power, we also have a lot of options there. We have hydro, wind, wave power, and we have solar cell electricity. We can use biofuels either from crop, from forest, or from waste, or we can use cellular organisms like bacteria that are making, for example, alcohol from sugar. When we come to the energy carriers for onboard storage, we have many possibilities there too. We have, for example, the regular diesel, we have gasoline, naphtha is a potential fuel. That's an intermediate component in the refinery process. Then we have methane, we have natural gas. Methane is the biggest component in natural gas. Then in natural gas there are also other components. Then we have liquefied petroleum gas called LPG. There are also a lot of different alcohols, for example methanol, ethanol, butanol, or dimethyl ether. So there's a lot of options coming here. We could also think of carrying energy in terms of hydrogen gas, or as is much in the air right now, in batteries. So what are the desirable properties of these kind of energy carriers? We have high energy density, which means long range. We have high refueling power, which means fast refueling. We have simple refueling, that we don't need to have safety precautions or complicated regulations to do the refueling. And we also need to have a low environmental impact so that we don't influence us as humans. We also have infrastructure question, that is the infrastructure ready for new fuels, or will we need to build up a parallel infrastructure? So coming to the question why we ended up with liquid hydrocarbons, they have the properties that they have excellent energy density, they have high refueling power, and good well tank to efficiency. And when we look at the different options that are available, we have the diesel fuel and we have the gasoline fuel, and the diesel fuel has a higher bar than the gasoline and the other, and the reason why it's higher here is because the engine that converts the chemical energy to transport energy is higher for diesel, and so the diesel engine is more efficient than the gasoline engine. That's why we get more energy out. And then when we go down here from gasoline to hydrogen, we see that the energy density is shrinking, and this means that the range measured per kilogram is decreasing, so we need to carry more kilograms to get the same range when we go down here. And in these cases, the lithium-ion and nickel metal hydride batteries, the lithium-ion and the nickel metal hydride batteries are already compensated for the fact that electric machines are much more efficient than combustion engines. Even though that we take this 3 times higher average efficiency here, the bars don't get as high as the diesel and gasoline engine. To my 2 favorite examples about why have we ended up with liquid hydrocarbons. In this example, we will look at the strength of the molecule bond, and we can start thinking about the fuel consumption, which is a volume over a distance. We're calculating liters per 100 kilometers. And liters, that's a volume divided by a distance, becomes an area. So we could think of the fuel molecules as a thin wire that is pulling the vehicle forward. When we do that, we wonder how thick is this wire, and relate this then to the force of the propulsion. A 1.5 ton car needs about 6 liters per 100 kilometer, so the area get to be 6 times 10 to the power minus 8 square meters, and the diameter becomes only 0.3 millimeters. These 0.3 millimeters is about the diameter of 3 straws of hair if you have really dark black hair, but if you have bright thin hair, then it's about 10 straws of hair. A 40 metric ton truck needs 30 liters per 100 kilometers. That diameter of that string gets double diameter, but that means 4 times the area. The main message here is that these strings are thin, so this illustrates that the chemical bonds are very strong. They contain a lot of energy. This shows the value of the liquid fuel that we are using right now. Next example is power fueling. We're standing at the gas station filling the car, and these are numbers from a previous car I had. I filled 55 liters of gasoline, and it took about 1 minute and 55 seconds to do the filling. And now when we're doing this filling, we're inserting energy into the vehicle, and we're doing it over a certain time. So this means that we are pushing power. So think of it as a power flow that goes through your hand while you're holding the nozzle. That's the power that we're getting into the vehicle. And how big is this power? Well, the heating value is 44.3 megajoules, and the density is almost a kilogram per liter. And if we just put these together, we get a power of 14.6 megawatt. So the power that flows through the hand while we're fueling the vehicle is 14.6 megawatts for a normal fueling. To put this in perspective, we can look at the world's biggest wind turbine from 2014. At that time, the biggest had 7.58 megawatt. So that would require 2 of these gigantic windmills to produce the full power going at their rated power. And the size of 198 meters and the diameter is 126 meters of windmill propellers. Coming to another perspective here, just to see how much these values representing current. So how big is the current if you would think of having a regular 240 volts single line? This it would mean 60,000 amperes. 60,000 amperes is an extreme amount of current. To put this high amount of current into perspective, 0.2 amperes kills a human. That would mean that we would be able to kill Linköping city twice over with this amount of current. A residential house usually have a 3-phase system with 16 amperes, so it's very far from the 60,000 amperes. Going back to the windmill analogy, we can look at the windmills that are going at their rated power, fueling the car. The car down there is a 3-meter big SUV, to put it in relation to the other components here. The main message is not that we should continue use this fuel as we have done for the last 100 years, but to show to you that we have a huge challenge in front of us. We need to respect the amount of engineering work that we have to do to find new solutions that can replace the system that we have been using so far. So we have a big challenge in the future. So I hope that you as students will participate and help us to find the solutions of the future, so that we can get access to the transportation that the society relies upon. Coming to the upstream energy conversions, we have a lot of things going on there. There's the manufacturing, pumping, transporting to the refinery, doing the refining, transport to filling machine, filling of the vehicle. For regular gasoline and diesel, this is not so much of an issue, but if we need to have pump pressurized gases, it will cost also a little bit extra there in the total energy system in the future. There's an intense research going on that is investigating all the different energy paths and all the different options that we have in the system. For example, what different ways can we generate energy? To electricity, can we go to other fuels, for example biofuels or hydrogen, or replacements on diesel and gasoline, and then later use them for the driving mission, where you can see the driving cycle that we have down here. The next step in the chain is the energy conversion inside the vehicles, and this is the core of the course here. We have many paths inside the vehicle. We have energy storages, it's the tank, battery, supercapacitors. We could also use mechanical energy storage devices or hydraulic energy storage devices. Then we have energy reformers, energy converters of different types. For example, the combustion engine is an energy converter, and the electric machine is also a type of energy converter, from electrical to mechanical. Finally, we have the power force to and from the transportation mission. When we have many options, we also have a lot of degrees of freedom, and these degrees of freedom can be used to optimize the fuel economy, and that is what we're doing in this course. Before going in, we will look at the demands from a well to miles analysis. So we'll go through some different energy paths and see why some have ended up as good candidates for solutions. We have a technology driver, which is carbon dioxide, that we would like to reduce, and there are also political pressure to reduce the carbon dioxide from transportation emissions. Here you see a plot showing the evolution over the years and the future legislations where we need to end up. So we see here from beginning of the millennium, we should, after 25 years, have halved that energy consumption. This is a very big challenge to do this kind of technology development to get down to these low levels. We turn back to the energy paths and we start to ask the question, what kind of solutions seem to be best to reduce the CO2? Before going into the different energy paths and looking at different solutions here with oil, natural gas, coal and hydrogen solutions, we will look at a motivating example that if you go electricity, but you don't go electricity up to the CO2 clean part, but you go over coal, you can have the situation as you have in China, where they have built a lot of coal power plants. And this was a picture I took myself in Beijing, traveling home from a conference in China in 2013, and you can see the yellow sulfurish color of the atmosphere. depending on where we take the energy from, has an impact on the environment that we get. Coming to the well to miles analysis, so now we're doing the backcasting. We have this vehicle here where we are requesting a certain amount of energy. If you have a gasoline engine, we go up, we have about 18% of average cycle efficiency, and then the refinery and transport, and we end up with 25 kilograms CO2 per 100 kilometer. And if we do the diesel version, we go with the vehicle and up, and we end up with 19 kilograms of CO2 per 100 kilometers. So it's a significant reduction if we compare it from the gasoline engine to the diesel engine. We have another option, and that is to use natural gas, which is done by a regular gasoline engine combustion system that has a slightly lower efficiency than but still it ends up with much better CO2 numbers than the gasoline engine. And the reason for that we will look at in a few seconds. But we will start to look at the other option, that we go all electric drive. So we take an electric machine, battery, grid, and as long as we have renewables and are working with renewable fuels, we have access to clean energy. But if we start to go the other way, for example, if we would go natural gas, we're still pretty well off. While if we would go for coal, then we're much worse even than the gasoline engine, even though that we're driving an electric vehicle. And if we look at the other options with electric machines, and we go fuel cell, so we go either with the hydrogen part, and we see that the hydrogen part is pretty good if we go through natural gas and we do steam reforming of the natural gas and then compression down here. While if we go from oil and we do onboard reforming of the fueling, then we are worse than the diesel engine, slightly better than the gasoline engine. And the same thing here is we would go from take natural gas into a power plant and do electrolysis. So the fuel cell could be an option if we go this path through natural gas, or if we could take electricity of the renewables. When we look at how to improve the fuel economy, we can do improvements on the big scale. We have the well to tank efficiency, that's upstream. We can do well to miles, the car parameters, mass rolling, aerodynamics, or we can do tank to wheel, which is the powertrain. The tank to wheel improvements are what we will be working with in this course. We will work with the peak efficiency of the components. We'll look at part load efficiency and look at if we can recover energy and optimize the structure of the vehicle, like using different components, for example, different types of hybrid. We can improve it by optimizing the structure of the vehicle by using, for example, series or parallel hybrids or complex hybrids. Another way is to use control systems to optimize the utilization of the different components that we have in the system to get as low fuel consumption as possible. So coming back here, we now have covered the topics in the total energy system, and I have pointed out that the most important part that we'll work with in this course will be from onboard energy storage out to the driving mission. And there's an interplay here. Depending on the driving mission, we can utilize different components inside the powertrain to get the best efficiency utilization of the individual components and best total fuel economy. Beside fuel economy, we have also other demands on vehicles. These demands are important factors for customers when they are buying their vehicles. Some of the factors that are important we will look at here, but the most difficult thing from an engineering point is that many of these performance and drivability factors are not easy to define and quantify, so that we can do computations and estimate how we are improving in the different directions. For passenger cars, top speed is one of the numbers that we are using to compare and buy vehicles from. We have also maximum grade, for which a fully loaded car can go to the top speed, and we have acceleration time from standstill to reference speed. Normally we have 100 kilometers an hour or 60 miles per hour, and we usually want to have like 10 seconds for a regular vehicle to deliver the performance that we're expecting. If you love performance, you can reduce the time, so for example 5 seconds or 4 seconds to reach 100 kilometers an hour. But we'll talk more about this in the lecture on Tuesday. So, that was it for today. After this lecture, we will have a query and answer session using Zoom that you can log into and start posing questions about the course. If you are thinking about some things or if you have some ideas, please join me there. We'll start this Zoom session at 12 o'clock